Hello again. In this video, we're going to start with the properties of matrix multiplication, Theorem 2. So if you let A be an n by n matrix and B and C have sizes for which the indicated sums and products are defined, in other words, if you remember, if you multiply two matrices, the columns of the first matrix better be the rows of the second. You have associative property works for any three matrices multiplied together, or with a scalar, D. A distributive property both ways, and the identity matrix and identity times any. So right here, the reason they have IM, because if you, A is an M by M, so this is I is an M by M. And then A would be a M by N. That would work. It would still be A. And this one is M by N, the other way around, and N by N. So it's still an M by N, both of them. So you have to be careful if you're on the left what the size of your identity is, but besides that, the identity times I will always equal A. Warnings though, it is not commutative. It does not hold. Commutative law doesn't hold. Let's look at example 7 for that. So if we multiply A times B, what do we get? Well, this is a 2 by 2 times a 2 by 2. So we should have a 2 by 2. And the first row, first column would be this first row, this first column. So that would be 5 times 2, which is 10, plus the 4 is 14. And then the first row times the second column would be 5 times 0. That would be the first row, second column here. 5 times 0, and then 1 times 3. How do you get the second row? So this is the second row, first column. So I take the second row, first column. 2 times 3 is 6, plus negative 2 times 4 is negative 8. So that would be a negative 2. And finally, just to show you one, right, again, that's the second row, second column. So it's 3 times 0 plus negative 2 times 3. So that's a negative 6. If I take B times A, well, I get the same thing. It turns out not. Because if we multiply these, what do you get? You get a 10, right? First row, first column, first row, first column. So you get 2 times 5, 10 plus 0. And this one would be first row, second column, first row, second column. So it would be 2 plus 0, which is 2. And then the next one is the second column, second row. Well, we're going to do second row, first column. So that would be 20 plus 9, 29. And then finally, I guess I'll show you one here. That's the second row, second column. So you take the second row, second column. So you get 4 times 1 plus 3 times negative 2. So that would be negative 2. You can see they're not the same. AB does not equal BA. It seldom does. So that is a warning. Actually, before I go on, there's 2 other warnings. A cancellation law does not hold always. So for instance, if you have A times B and A times C in algebra, divide both sides by A and get B equals C. Well, not true in general. You can see in the next section in 2.2 that if it's invertible, then yes, you can do that, but not in general. If the product AB equals 0, you cannot conclude the same thing, that A equals 0 or B equals 0. And if you look at these exercises in the book, they show you some counterexamples where it actually just does not work. And again, you'll look at the conditions in the next section to show you when that can happen. There's 2 other things in this section. One is the power of a matrix. What if I had, by the way, if you're going to take a power of a matrix, you need to have an n by n matrix, because you need to be able to have those inner things O is the same. And if you have a 2 by 3 multiplied by a 2 by 3, well, that's not going to work, is it? So you need to, so let's just do an example here. You need to have a square, what we call a square matrix. And k needs to be a positive integer, and then you have this formula just like you would as a power exponent. So let's just do a simple example with that. If you're looking for a squared, that would be a times a. And you can see that this would work because this is again a 2 by 2 by another 2 by 2. The answer would be a 2 by 2. And what's the answer going to be? Well, the first row, first column, first row, first column, what is that? First row, first column is 1 times 1 plus 2 times 3. So that would be 7. The next one, first row, second column, what would that be? That would be first row, second column, so it would be 1 times 2 plus 2 times 4. 8 plus 2 is 10. So again, I will just do these two. This one is going to be second row, first column, so second row, first column. So 3 plus 12 is 15. Then first row, last column is 6 plus 16 is 22. So that is an example of powers of a matrix. The transpose of a matrix. Sometimes we'll need the transpose. Given an n by n matrix, the transpose of a matrix, the transpose of A is the n by n matrix. You flip it. The rows are the columns and the columns are the rows, denoted by A sub t. So in example 8, what is A sub t? That becomes AB. The rows become the columns. CD. And the columns become the rows. So the size didn't change for A because it was a square matrix, but B, this is actually a 3 by 2, so this should become a 2 by 3. What does it become? Well, the columns, the rows are the columns, or the columns are the rows, so this would be negative 5, 2. The next one would be 1, negative 3, and 0, 4. So see if you can do CT. Pause it. What's the answer? There it is. Makes sense. This is a 2 by 4, so this is going to be a 4 by 2. The rows are the columns, and the columns are the rows. Here's all the properties for transpose. The transpose of the transpose, that could be easily shown, is the original. That makes sense. And if you add two transposes together, that's easy to be shown. That is the transpose of each. Take a scalar, you could just take it out. But D is kind of interesting. If you do the transpose of the two things, and you can kind of see that from the mappings that we did last in the last section, or in the beginning of this about the multiplication of composition functions with a matrix multiplication of our standard matrix. You can see that it does make sense that they're switched. So last thing we're going to do is look at a practice problem with that. These can actually be proved, and some of them are left for the book for you to do, but I think the last one you can find in one of the exercises. Okay, so let's try a practice problem with this. So this one, they want you to multiply first. So if we take A times X transpose, you have to multiply first. So what that's going to be is A times X. and then the transpose. So this is a 2 by 2. This is a 2 by 1. So our result is going to be a 2 by 1. We still haven't transposed it though. We'll do that after. So this would be just a matrix time a vector. We've done that before, so that's 5 and a -9. And then the next one would be -10 plus 12. So if you transpose that, then it would become a 1 by 2. And the rows are the columns and the columns are the rows. So you would get a -4 and a 2. Okay, so let's see if we take xt and at, which is what the theorem says, if we get the same thing. So what is xt? Xt would be 5, 3. The transpose first, and we're going to flip the order. A transpose, what is that? That's going to be 1, -3, and then -2, 4. If we multiply that, this is a 1 by 2. This is a 2 by 2. So you do get a 1 by 2, so that part's good. And what do we get? We get a 5 with a -9. We do get a -4. And then the first row, second column, -10 plus 12 is a 2. You do get the same answer. Practice the others. I'll just give the answers to those. And here is the next two. Notice how x times x transpose is, x was 5, 3, so the transpose would be 5, 3 this way. The column becomes the row. And this is a 1 by 2, and this is a 2 by 1. Oh, sorry, that's before. This is actually a 2 by 1, sorry. This is a 1 by 2, so the answer is a 2 by 2. That's confusing. I looked at the wrong one there. Let's draw lines there so we understand where those separate. And you can see that that works. Versus the other way around, x transpose times x is actually just 34. 1 by 2, it does make sense. This is a 2 by 1, so the answer is a 1 by 1. And to get that, you just take 25 plus 9 there, which is 34. You do not need to write that in matrix, so the answer is, if it's a 1 by 1, it's just 34. Finally, what's A transpose times X transpose? Try that one. You can pause it, then try it. Make sure you get it. I think that's what we want. Yeah, there's something wrong with this, isn't it? If you look at this, this is a 2 by 2, and this is a 1 by 2. You can't even figure this out. This is undefined. And then they ask, is ATXT defined? And the answer is no. It's undefined. And that concludes this section.